You know what I'm saying? Compound probability, you know what I'm saying?
All right, in the last set of notes, what we ended up really doing was focusing on the idea of counting combinations and permutations and just all the different available options that we have. Today's notes are going to be more in the direction of the probability. What are the odds or the chances that you're going to get a certain thing? Okay, now we're going to talk about what these different formulas are in just a minute, but what I want you to notice at the beginning is that there does seem to be a good amount of multiplying. Okay, this does not say P times A, which is how we normally see it in algebra, but this is the probability of A. It refers more to what's called function notation, and you'll be better at that after algebra 2. Okay, but this is the probability of A multiplied by the probability of B. This is the probability of A multiplied by the probability of B given A. That one sounds kind of crazy, and it'll sort itself out a little bit later. But what I do want you to see is there's a sense of multiplication in this. Now, what I'm going to do is I'm going to go back and I'm going to look at the deli problem that we had in permutations and combinations. The very first question asked asked how many different lunch specials are possible. And to do that, you just multiply all your different options together and you get 120. Now, we could rephrase the question as a probability question and say, what is the probability that you will choose a ham and turkey sandwich with potato salad with juice? Right? We can ask you, what is the probability of selecting a very particular order? Well, what we had figured out is that there's 120 different orders. So the probability of getting a very select group, let me just circle some of them here. I forgot what I did. We'll just circle these 3. You might not even be able to see this. Anyhow, I circled a few of them there. All right, the probability of choosing that, of course, is going to be 1 out of 120 because there's 120 different ways you can do things. Now, how would that calculation have been created to get to this as the fraction? You would just treat each of these as a probability. You have a 1 out of 6 chance of choosing ham and turkey, which multiplies by a 1 out of 4 chance that you're going to choose potato salad, multiplied by a 1 out of 5 chance that you're going to choose juice. Okay, so in a way, what we're going to do with probability is almost like just taking the reciprocals of numbers and then multiplying those together. So what we begin with here is independent events versus dependent events. Okay, what we are looking at is the probability of 2 or more things happening and what's the overall probability that those 2 or 3 things will happen in a sequence or togetherness with each other. Like at the beginning here, we want the probability of A and B. Like the probability that A is going to happen and B is going to happen. That you're going to choose a ham and turkey sandwich and you're going to choose potato salad. Okay? Independent, dependent. Independent is a case where one event does not affect the next event. Now, this gets a little bit tricky because if we're talking about ordering meals off of the menu, you might say, well, if somebody orders a ham and cheese sandwich, they're not going to order blank to follow because it doesn't make sense. But you got to separate yourself from that. Okay, so let's do a different example here. Flipping a coin. Okay, if you have a coin and you flip it, it either lands on heads or tails. Okay, so suppose that we flip it twice and we're asking the question, what would be the odds that we flip heads and then we flip heads again, back to back? The main thing about this is when you flip it the first time, whether it lands on heads or tails, you pick up that coin again and you flip it, what it lands on the next time had nothing to do with happened on the first. So just because maybe it landed on heads the first time doesn't mean that it's going to be more likely to land on tails the next, right? The coin doesn't have a consciousness that says, oh, I probably shouldn't do heads twice in a row. Okay, so there's these things that are called independent events where the next event is not affected by the previous. Okay, then there's dependent events where that does occur, where what happens in the first event affects the other one. The most classic example of this one is going to be drawing things out of a bag. Okay, so suppose you had a bag of, I think we did marbles before. If you have a bag of marbles and you draw one marble out, okay, maybe you get a red marble. Instead of putting that marble back into the bag, if you take that marble and you set it to the side and then you draw again, because if that marble isn't back in the bag, the number of marbles has now changed and the number of maybe red marbles has changed. So the second event is affected by the first. All right, so independent events, if they don't affect each other, you just take their individual probabilities and you multiply them and it gives you the answer, which is like what I showed you in the deli menu thing. All right, a dependent event, you're going to multiply them again, but the odd thing is that the second probability is going to be affected by whether or not the first one occurred, that happened. So the probability of B, it's not just probability B, it's probability of B given that A has happened, that it's actually occurred in the previous one there. So all right, so for example number 1, we're going to do 2 different problems, and one of the problems is going to be an independent problem and the other one is going to be dependent. So I think using the same like context problem is a good way to do this, because you get to see how they are actually different than each other. All right, what we have is a desk drawer that has 5 red pens, 6 blue pens, 3 black pens. Then it has 24 silver paper clips and 16 white paper clips. Okay, so we've got pens, but we've also got paper clips. All right. All right, first question. If you select a pen and a paper clip, so one of each, without looking, so you just kind of reach in the drawer and you pull them out, what is the probability of selecting a blue pen and a white paper clip? Okay, now, the type of paper clip that you select has absolutely nothing to do with the fact that you may have chosen a blue pen. Right, when you choose that pen, it's like, I grabbed a pen, because you feel it by size, right? You pull out a pen, you set it down, right? And then you go back and you reach in there for a paper clip. The paper clips is a whole different like group. You might as well reach into a different drawer. So this would be an example of independent events. They do not affect each other. Okay, so the probability of drawing a blue pen is going to be 6 out of the number of pens that we have, which I believe is 14. That's what it looks like. I hope I'm adding all that up right. All right, so you have a 6 out of 14 chance, or 6 out of 14 probability that you would select a blue pen. Okay, and then next, when you draw from the paper clips, we want a white one. That's going to be 16 out of the total number of paper clips, which is going to be 40. Okay, so what we're doing is taking their individual probabilities and just multiplying those together. I could probably do that as a little bit of mental math, but I think I've already talked enough that I'll just type stuff in and just give you the answers that way. And obviously you got even numbers, so you could reduce a good amount of this as you go. All right, turns out to be that is a decimal on the calculator. Pretty easy to change it back into a reduced fraction. So it's also going to be 6 out of 35. You can state the answers either way. It doesn't really make a difference. The one thing that I would have you do, though, is if you're going to be taking this number here, even though it's a correct answer to state it as a decimal, I think it's a nicer way just to shift the decimal over and go ahead and put the percent symbol on there. Because if you can see the percent symbol on there, we know that we've actually changed it to percent. But if you leave it in a decimal, which would require you to not have the percent symbol, people tend to get a little bit confused on whether or not it's already been like converted. So safe bet is always just to do that. Fractions are good as well. You do that. All right, so that is the title here is compound probability. I want to say combined, but that is the compound probability of drawing a blue pen and a white paper clip. All right, so our other one, what we want to do is look at a dependent situation here. So let's see how that works out. We're going to select a blue pen, 6 out of 14. And we're not going to look at paper clips. We're going to draw another pen. Okay, so if we reach in, we don't care about the paper clips at all anymore. We reach in, we pull out a pen, and it's a blue pen. We set that one on the table. It's there. That means that when you go back to the drawer to pull out another pen, you don't have 14 pens in there anymore. You've only got 13. Okay? What do we want? We want a black pen. Then there are 3 black pens. Okay, so this is the concept of dependent. If I were just looking to draw a black pen out, just to draw a black pen out, it would have been 3, I can't see that on there, it would have been 3 out of 14. It would have been 3 out of 14. But because this event is following another event, and it's affected by it because we're still looking at pens, the denominator has changed, which is, of course, going to totally change the answer to the problem. Okay, so let's see what that one looks like. And all right, so we're going to get that, which I don't know if it's going to look much better as a fraction. Yeah, it's not too bad. All right, so as a fraction, you get a 9 out of 91, which is the same thing as about 9.9%. And you can get there. I want to bring up this other one here just so that you know it. In this case, so it was dependent. I'm still going to talk about a dependent one. Sometimes you get asked the question, what's the probability you'll draw 2 blue pens in a row? If you did that, then it would still start with 6 over 14, but if you wanted another blue pen, the numerator is also going to change. So instead of doing like another 6 over 14, you'd end up doing a 5 over 13. Okay, so sometimes you like switch, in this case it's colors, you switch colors. If you don't switch colors and you want to do like repetition of the same thing, then you're going to see changes in the top and also the bottom. All right, next what we're going to do is talk about the differences between mutually exclusive events and overlapping events. So in the last set of notes, we had to talk about combinations versus permutations. In today's notes, we had to talk about independent versus dependent. And now we talk about mutually exclusive versus overlapping events. All right, now next, what I want to do is address something about wordage that would be on here. When we're talking about independent and dependent events, these are all cases where you want one event to happen after another event. And when we write these out, we call them the probability of A and B, like these two things both happening. And that turns out to be a multiplication problem that you have to do. All right, in the next part, where we talk about exclusive and overlapping events, these are all going to be referred to as A or B. Like, it doesn't matter if we get an A or a B. So it's not about getting A and B both happening, but that we're okay with getting either one of those. So it's actually the word or. You can see here I actually had a typo, and because those words are so important, I actually identified pretty quickly that I had copied and pasted, and I was like, wait a minute, it's supposed to say the word or here. So these are both or, and the operation that you see when you do the calculations is actually going to be an addition. So you do need to make an association that the word and is going to be multiplication, and the word or is going to be an addition problem. All right, mutually exclusive events. A or B, they are totally different than each other. They're just separate things that exist, okay? Overlapping events says that A and B could be different than each other, but there can also be like the same of them. Now, the image that I always have in mind here are Venn diagrams, but I don't know if you've studied Venn diagrams this way. Let me think. I can make up an example right now. The Venn diagram for overlapping events is going to have the two circles that are on top of each other. All right, and mutually exclusive are going to be two circles that are separate from each other here. Exclusive things could be like, you know, one circle could be birds. The next circle could be fish, birds and fish. Okay, what is the probability that we randomly select an animal and it's a bird or a fish? These are completely different things, okay? So what you do is you take their individual probabilities and you just add them together. Okay, if you have an overlapping situation, there's a chance that something's the same. Consider a deck of cards. All right, a deck of cards, you could have an ace, and you could also have ace spades. All right, so if we asked you the probability, what's the probability of drawing an ace or ace spades? Okay, well, there's a little bit of overlap because there's one card that happens to be an ace of spades, right? There's one card that's both of them, but then you've also got cards that are just aces and you've got cards that are just spades. So when you get to the overlapping, you have to be careful. Here's the key thing. You have to be careful that you are not double counting something. So if you have this overlapping situation, you can take the probability of A. So for aces, it would be 4 out of 52. I didn't think about cards for a second. Yeah, you have a 4 out of 52 chance. To get a spade, you would have 13 out of 52. Okay, but you have to be careful that you don't just add those two things together, because there's a particular card that showed up in both of those categories called the ace of spades. So then you need to subtract the amount that's in the overlapped area there. Example number 2 is going to address the mutually exclusive type probability. What we have here is a pie chart of different sports for the fall seasons. All right, it appears that student athletes at a local high school may participate in only one sport each season. It's so unfair, isn't it? All right, they only get to choose one sport, which actually makes the problem really easy for us, though. That's why we like it. All right, what is the probability that a randomly selected athlete plays volleyball or, see that keyword there, or is on the swim team? Okay, so for that, we get to do the probability. Let's change our letters up here because we can. The probability of volleyball, so probability of V, plus, because it's an or case, the probability of swim. Good, that's the only one that starts with an S. All right, so what you do is you get to choose, you get to take their individual probabilities and then you just add them together. In this case, these are all presented as percentages here. Basically, like if you randomly select a student and that student plays basketball, and you choose somebody who's playing sports, you choose a student who's playing sports and they're playing basketball, you had a 28 out of 100% or 100 chance that you would have selected that student. So your fractions are already as percentages here. Anyhow, volleyball is 10%, and swim team is 24%. So you have a 34% chance of selecting a student that's either here or here. All right, math should seem pretty simple. Again, like some of the other things that we're doing, it's really looking at the details and definitely getting, definitely figuring out whether or not it's going to be a mutually exclusive or an overlapping. Right? Most of the time, people are comfortable with doing the mutually exclusive. You got to be really careful to notice if you have an overlapping event and just make sure that we take out the extra that we've got. Otherwise, or other than that, the calculations aren't too bad. All right, so then example 3, this should be an overlapping event. The cases that we got to be real careful of. All right, what is the probability of rolling either an even number or, there's that word again, an even number or a multiple of 3 when rolling a standard die? All right, when you roll, so that's just a regular die. The choices that we have are going to be 1, 2, 3, 4, 5, and 6. I shouldn't say choices, but they're going to be the outcomes. Can either be a 1, 2, 3, 4, 5, or 6. All right, we've got 2 events that we're going to be looking at and the or situation. So there's going to be this adding. We got the probability of an even plus the probability of a multiple of 3. Just abbreviate that there. Okay, so the probability of getting an even number is going to be 1, 2, 3 out of 6, which obviously is going to reduce down to 1/2. Half of the numbers are even. These are going to be as fractions, of course. Different than the last problem. The probability of getting a multiple of 3, that's anything that is divisible by 3. So you get 3 and 6. So for that, you're going to get you get 2 out of 6, which is the same thing as 1/3. All right, but the key thing here is that when we did that, one number actually got counted twice. Right? When I do the even numbers, I'm looking at the 2, the 4, and the 6. When we look at multiples of 3, you get a new number here with that one, but the 6 is a double counted number. So what you need to do then is subtract the probability that we have an overlapped event. Okay, and that happens one time. There's one time where we double counted, one time out of the 6. Let me get that. All right, so I now realize that reducing these was not the best idea because I want to have a common denominator anyway. All right, so you win some and you lose some. All right, so 3 out of 6 plus 2 out of 6 minus 1 out of 6 is going to give you 5 minus 1, which is 4 out of 6. And now you can reduce down to 2/3. Yeah, there's an example of reducing not helping out, huh? At the beginning there, but not too hard to fix. Okay, so in the end, it ends up being 4 out of 6 or 2 out of 3. Now, if you go back to the list, so what I'm trying to talk about right here is that if the subtraction part didn't quite make sense, going back to the list, we can still see that, like, of all of our numbers that we had here, let's use a different color. The even numbers, right, are those. And anything that's multiples of 3s would be 3 and then 6 again. So out of all of those, we ended up selecting a total of 1, 2, 3, 4 of them. The only 2 that don't work for our OR situation is going to be the 1 or the 5. So we still end up with the 4 over 6. It's a bit of a tricky thing to understand, but if you just add them individually, so if you can use the formula, which is useful, when you add them individually, we're double counting something. In this case, we were double counting the 6. So we need to make sure that we remove the 6 one of those times. All right, so we only subtract it once because it counted twice and then it all balances out.